Riccati equation and propose the bisection method with SDA for acquiring the optimal control output. In the second part, I will introduce the quadrotor at infinity control, which include a dynamics model and a controller design. In the last part, I will show the simulation results, which include the position velocity, Euler angles, and angular velocity. Besides that, I will show the performance of the structure-preserving doubling algorithm. So this is the general form of the H-infinity control problem, where X is the system state, Y is the measured output, W is the exogenous input, for instance, disturbance, U is the control input, and Z is the performance output. Sometimes we call it the penalty error, which is designed to be minimized. The goal of the H-infinity control is to stabilize the system while ensuring that the supremum of the penalty error divided by the disturbance is bounded under gamma. In a nutshell, H-infinity control attenuates the gap between the disturbance input W and the measured output Y. At the middle of this equation, the transfer function T maps the input disturbance W to the measured output Y. In other words, it minimizes the H-infinity norm of the transfer function. Further, with this assumption of C2 and D21, a simplified form called the state feedback H-infinity control is given as follows. As you can see, the measured output Y is directly equal to the X, and that is the reason of its name, the state feedback H-infinity control. It is well known that the control input designed to solve this problem is given by the following, where X is the solution of the continuous time algebraic Riccati equation for KER with the following Hamiltonian matrix. It is well known that the Hamiltonian matrix is strongly related to the KER equation. And given a Hamiltonian matrix, we can find a continuous time Riccati equation that mapping a Hamiltonian matrix to the X solution of this linear metric equality equation. By the bounded real lemma, we know that the H-infinity norm of the transfer function must be bounded under gamma, and the eigenvalues of the Hamiltonian matrix must not exist on the imaginary axis. Also, the solution X of the Riccati equation generated by the Hamiltonian matrix must be positive definite. There are several traditional methods for solving the KER. First, QR algorithm, which treats the KER as general eigenvalues problem, which is adopted by MATLAB's implementation's built-in function called KER. Structure-preserving algorithm utilize the symplectic transform property, which provides better accuracy to the solution. Doubling algorithm using this idea similarly to the iterative point method can provide doubled convergence sequence with better convergence speed. And finally, matrix sign function method is an iterative-based algorithm which is numerically stable. In this paper, we adopted the structure-preserving doubling algorithm proposed by Professor Wenwei Lin's team in 2005, which combined the idea of the structure-preserving algorithm and the doubling algorithm. It has competitive accuracy and faster convergence speed. This page demonstrates the pseudocode of the structure-preserving doubling algorithm, and the detail will not be covered in this presentation. Recall that computing the optimal H-infinity control input requires finding a KER solution X such that the supremum of the penalty error divided by the disturbance input must be bounded under gamma. The solution to this is to combine the SDA and bisection method for searching. So here, we first initialize a lower bound and a upper bound of the gamma. And at each iteration, we shrink the searching interval to half of the origin. We construct a new Hamiltonian matrix to this gamma, and using the structure-preserving doubling algorithm to calculate the solution X of the list of the Hamiltonian matrix to generate the KER. If the residual of the solution is lower or equal to the setup precision, we then update the new solution X and the upper bound of gamma. Otherwise, we update the lower bound of the gamma. This procedure will be repeated until the algorithm converges. Next, I would like to introduce the model of the quadrotor. In this paper, we parameterize the rotation of the quadrotor with Euler angles, and the rotation matrices are given as follows. There are 4 governing equations for the quadrotor model. The first is the transformation between the angular velocity and the Euler angular rate. The second is a velocity equation, and the third is a torque equation, and at last is a force equation. The complete dynamics of the quadrotor can be now derived from the aforementioned 4 equations. Now we can define the state variable, disturbance input, and control output as follows. The matrix A, B1, and B2 can now be obtained by linearization. The matrix C1 of the penalty arrow Z is designed as follows, and the control input penalty matrix T12 is given as follows respectively. Additionally, a feed-forward term is designed for compensation since the gravity term, which is constant, can be vanished in the process of linearization. To sum up, the final control input equation is given as follows. Now I would like to show the simulation result. First, we have the parameter set up for the quadrotor and the gain or the weight of the H-infinity control. We let the quadrotor track a circular trajectory given by these equations. The desired rotational states are set as follows. Additionally, we add some randomized disturbance to the force and torque. In the left chart, we can see the position tracking result of the quadrotor, and at the right side, we have the velocity tracking result. The blue line indicates the true state of the quadrotor, and the orange line indicates the set point of the system. In the left side, we have the Euler angles or attitude of the quadrotor, and at the left bottom side shows the yield angle of the quadrotor, where the arrow or the angles only have minus and plus 2 degrees of fluctuation. And at the right side, here shows the result of the angular velocity. Finally, I would like to demonstrate the performance of the structure-preserving doubling algorithm, which is the reason we are using this algorithm. At the left side, the KER residual has the precision up to 10 to the minus 7 power precision. And at the right side, we compare to the MATLAB. The orange line demonstrates the time cost of the MATLAB built-in function named KER, and the blue line shows the time cost of the STA. The STA is 4 times faster than the MATLAB built-in function. This is the end of my presentation. Thank you for listening.